So allow me to share my screen on that particular note in Canvas, which we have already talked about a few minutes ago. Okay, so for this topic, we'll be using trigonometric transformation. So what is it really when we talk about trigonometric transformation? You are to recall previously learned concepts in trigonometric identities, and you are to, of course, apply together with trigonometric identities the rules, the techniques that you have already learned in the past. And what are these techniques? So number one is the very basic power rule. And second is the method of substitution, together with the 6 integrals involving simple integration, or simple rather trigonometric functions. Now, other techniques will apply like rules of exponents or trigonometric building and logarithmic function or exponential function, as long as you have first transformed these complex trigonometric functions into simple expressions, which allows you already to apply previously learned concept in integration. So type 1 here, type 1, as you could see, I will have this enlarged so you will see better. So let me just know if it's not clear to you. Okay, too big. Okay, I think that's better. So the first type in here is actually the simplest of the 7 types, or the 6 types of the trigonometric transformation techniques. And this involves either a sine or a cosine function. A single function, which can either be a sine or a cosine. And we have 2 cases under this particular type 1, which requires trigonometric transformation. Case 1 involves a sine or a cosine function wherein your n here, as you can see, this n, in which your sine or cosine function is raised to, is an odd positive integer. So meaning you cannot use this particular transformation technique if n is negative or if n is even. So it has to be both odd and positive. So what is the thing that you will do prior to integration whenever you're given this particular trigonometric expression? So what you're going to do, as suggested, is you split your sine x raised to n, or your cosine x raised to n, into a sine raised to n minus 1 x, sine x, and use the identity of the sine in terms of the cosine. So you've learned from your basic trigonometric identities that the sum of the square of the sine and the cosine is 1. So we will use this transformation after you have already split your sine or your cosine function into one that contains a sine and the rest is raised to an even exponent. I'm saying even because once you already took the sine function, let's say, for example, from a sine cube, what remains is a sine squared. And that sine squared should be changed to 1 minus cosine squared of x. Now, I think it's already forthcoming, or it's already a given, that after you have transformed your sine squared of x to 1 minus cosine squared of x, you need to multiply it with the sine of x here, which you have set aside. This sine of x will stand for the derivative of the cosine squared of x here. And if it's multiplied to 1 in here, then that's directly integrable. So split your sine or your cosine function, which is raised to a positive odd exponent, into one which has an even exponent and the other one is odd. That particular function, which is odd, should have an exponent which is equal to 1. That will represent the derivative of your function raised to an even exponent after you have used this particular identity in here. Now, if you're given a cosine raised to n function, then this would be cosine squared x equal to 1 minus sine squared of x. Okay, so your identity will be different, of course, because this one in here, in that direction, it's using a sine. So if it's a cosine, we change this also. Okay? Now, as an example, you have this example. You have cosine cube x dx. So your n here, which is the exponent of the cosine, is 3. So your n here is equal to 3. It's positive and it is odd. So as suggested, you split this cosine cube x into cosine of x and cosine squared of x. You subtract 1 from this. Okay. Now these two, when multiplied, will of course be still equal to the original given function, which is the cosine cube of x. Now, just like what is suggested, this cosine squared of x, you will express in terms of its equivalent identity, 1 minus sine squared of x. Now, this is your cosine. Now, you will substitute next, or rather not substitute, but you will distribute next the cosine of x function here to the 1 and the sine squared of x, yielding this integral that you have in here. The purpose is, for this one, it's readily integrable to the sine of x, while this one, the purpose of the x is to stand or represent the derivative of the sine of x. Because in here, you're using already substitution. Your u is the sine of x, and it follows that its du is the cosine of x dx. Your n is equal to 2. So you're now to apply here for your u, which is sine of x, power rule. So if you're going to use power rule to this, because you already have the du, which is cosine of x here, dx, then that would be sine cube of x divided by 3. Power rule dictates that you should have u raised to n plus 1 over n plus 1. So that's the thing that you are seeing in here. Do you follow? Do you get it, class? Okay, so since everybody is silent, I will assume that it's clear. Now we go down to the second example here. So one, we have here cosine. This time we have the sine. Okay, so the same thing. You set aside one sine function and you subtract 1 from the exponent of the original sine. That makes it sine to the 4th of x. Then you have sine of x dx. Okay, now this, if multiplied, would still be sine to the 5th of x, or sine x raised to 5. Now your sine x dx is still the same in here. We did not touch it. Your sine to the 4th x, or your sine x raised to the 4th, is actually equivalent to the sine squared of x squared. Sine squared of x squared is sine to the 4th x. What is sine squared x? That's 1 minus cosine squared x. Okay, so this is the equivalent identity, or the Pythagorean identity, 1 minus cosine squared of x, which is equal to sine squared of x. Since this is squared, you should also square this one. And you do expansion. So if you'll have this expanded, you will have 1 minus twice the product of these two. So 2 cosine squared x and the square of that, which is cosine x raised to 4. And again, distribute the sine of x as a multiplier to these 3 terms you have in here. So your first term will be the integral of sine x if multiplied to 1. So the answer of that is cosine of x, which is negative. Now for this one, this will also be using substitution together with power rule. Your u here is the cosine, your n here is equal to 2. This is the du. Okay, this is your du. The same thing happens to this. It will also use power rule with substitution. So if you use power rule for this one, knowing that the derivative of the cosine is negative sine, so you make use of this negative here for to go with your sine x dx. So you just use power rule for cosine squared of x, which is cosine cube of x divided by 3. The 2, which is a constant, is simply multiplied to whatever is our answer here after we use power rule. If you use power rule for this one, it will become negative because in here your sign is positive. So you need to place negative here and negative as well on the cosine. So power rule for that will yield cosine of x raised to 5 over 5 with the, of course, the sign being negative. So in here we have case 1. Okay, let me clear my markings. So this is case 1. This is case 1, class 4, type 1. Okay, now what is case 2? Under type 1 still, so it's still type 1. So case 2 is when n is an even positive integer. This one, n is an odd positive integer. This time, case 2, n is an even positive integer. Still positive, but this time it's even. Okay, even. Now, you will be using a different identity here. So again, I'd like to emphasize for case 1, you're using this identity or the cosine squared of x equal to 1 minus sine squared of x. In here, you will be using this double angle sine identity. I say double angle cosine rather identity. You see here cosine, the cosine function with a double angle. So its angle is times 2. So it's a double angle. The only difference of the sine squared x from the cosine squared x is that for the sine, the thing that separates the two terms in the numerator is minus, or the sign is minus. For the cosine, the two terms in the numerator is separated by a plus sign. Okay, do you follow? So case 2 requires that you use a different identity. And how will you use these identities? So you have 2 examples as well here. So we'll look into the first example first. Okay, now that's the first example. The sine squared of x dx. So sine is raised to a positive even exponent. The equivalent identity of this is this. So you have this one. Now from here, you can split the two terms in the numerator by distributing the 2 in the denominator. So 1/2 dx for the first integral. The second integral will be 1/2 cosine of 2x dx. Now this one will yield 1/2 x. And this one, it's just using the basic trigonometric integral of the cosine. The only difference, class, in here is that your theta is 2x. So it's du. So if this is cosine u, the du should be 2 dx because your u is 2x. So the derivative is 2 dx. So you need a 2 in here and you need to multiply by 1/2 before your integral or outside your integral. That way you did not alter the original. So your original 1/2 constant here becomes 1/4, as you could see here. And we apply the integral of the cosine, which yields a sine. Okay, so we use this identity here, the double angle cosine for sine squared of x. Do you get it? Any questions? Okay, so I will clear the markings if there aren't any questions. So we go to number 2. This time number 2 is a cosine. It's raised to a positive even exponent. So you will write the equivalent identity of that, which is 1 plus cosine of 2x divided by 2. Since this is to the 4th, this must be then cosine squared of x squared. And as such, we have this in here because the cosine squared of x alone is this one. Okay? Now, so you will also have this expanded. The algebra dictates that you will expand the exponent and you will square this one. So this becomes now, class, by the way, this one becomes 1/4. So there's an error here, a typo error. This should be 1/4. And if this is expanded, you will have 1 plus twice the product of these two plus this cosine squared of 2x, because this will be squared. Okay? So in here, everything here will be multiplied by 1/2. Why it should be multiplied by 1/2? Because there's a lacking 1/2 times 1/2 in here. This should be 1/4. So we just multiply everything by 1/2. Then this entire expression would be the same. We don't have any problem with the first term here. So the integral of 1 dx is 1/2 x. The integral of cosine 2x, just like this one in here, will be cosine of 2x times 2 dx. That should be the integral for it to yield a sine of 2x. So we need this one. This is actually part of the derivative of the 2x, which is 2 dx. So you will yield here the sine of 2x. Okay, so the integral of this will be the sine of 2x. So this will also be multiplied by, again, 1/2. Okay, because we're answering already. For this one, there's a need for you, again, class, to distribute 1/2, or rather 2 in the denominator for the 1 and the cosine of 4x. So if it's integrated, this will be 1/4. So you have 1/2 times 1/2, so 1/4 x. And this one, the cosine of 4x will need a 4 dx for its du. And as such, it needs 1/4. So you see this 1/4 in here? Now this 1/2 times 1/2 is this 1/4. This 1/4 that you see here, the other 1/4 is for the derivative of the u in your cosine function. So you need to add, you either need to multiply by 4. That way you can integrate this right away. So multiplying by 4 requires that you multiply by 1/4. So the integral of the cosine 4x is the sine of 4x. So all of your answers here, by the way, should be multiplied by 1/2, because there's an error here, a typo error. It should be 1/4. Now you see a 3/4 here because this one and this one were combined. So 1/2 plus 1/4 is 3/4. Then you have 1/2 sine of 2x, and you have here 1/4 times 1/4, 1/16, the sine of 4x plus c. So you just follow the procedure of properly using, so I say properly using the identity for that particular case that you are dealing with, that you need to transform. So this would be the identities that you will be using for the sine squared of x and the cosine, or rather the sine of x raised to n and the cosine of x raised to n, where n is any positive even number. Now, I'd like you to process what I have given you and discuss to you. Do you have any question under case 2? So the usual way of expanding, of using power rule, of using substitution, that way you can apply power rule together with the basic integral of trigonometric functions will be applied. Do you have any questions here in the 2 examples? None? Okay. There are no questions. I have a question though. How will you convert this one? What's the equivalent identity of sine 1/2 x raised to 4? If you don't have your microphones on, you can use the chat box. How do you convert? This is a function which is raised to a positive even exponent. So I'm asking, how will you convert this first, or have it transformed first? That way you can have it integrated. Anybody? Drews, do you have any idea how do we write the equivalent identity of this using case 2? Drews Aujero.
Excuse me. Ano, Mas?
How would you write
Tadra.
the equivalent identity of this one? Would you know the sign of 1/2 x raised to 4?
Identity, Mas.
Yes, you will transform it into an identity that we discussed just a few minutes ago. Case 2, how will this be transformed into its equivalent identity? That way we can have this integrated. Okay, what about Kesselberry? Would you know the equivalent identity of sine 1/2 x raised to 4? The reason why I'm asking you this class is you don't expect that your integrals will look like this, in which the argument is just always x. What if the argument or the angle is not x? In principle, you're still going to use the same conversion to have it transformed into a trigonometric expression that you can right away integrate, or you can use power rule or substitution. Now, in mathematics, it's not always something like this. If the formula given to you like this, what is important is you understand why the formula is like that. So I mentioned a while ago that we call this the double angle cosine, equivalent of the sine squared x. And we call this as well the double angle cosine, equivalent of the cosine squared of x. So I will ask you then, if you're going to use the same principle as illustrated here, in the sine squared x and in the cosine squared x, what should be the equivalent identity of the sine squared, or rather the sine of 1/2 x raised to 4? Because don't expect me that I will give you something like this as well. It will be an application of the examples that you have in here, but never will it be similar to the examples. Because if it will be similar to the example, then I haven't taught you the principle of application. I have simply taught you how to memorize. So that's the reason why I'm asking. So now I go back to my question. If this is called the double angle cosine equivalent of the sine squared of x and the cosine squared of x, how will you then transform the sine of 1/2 x raised to 4? Have you noticed what happens to the angle here? I've mentioned double angle cosine. What happens to the angle? What happens to the original angle? Kyle, Biko. What have you
It is divided by 2, miss.
What happens to your angle here when you write it already in this particular equivalent identity? Got times 2. Very good. Eugenie Lopez. The reason why this is called the double angle cosine equivalent of the sine squared x and the cosine squared x, it's because the angles double. So you have x here, it becomes 2x here. So was this not taught in high school? The formulas should be given to you at the same time how you apply the formula as well. It's not just that you're going to simply memorize the formula. So this identity tells you that whatever is the angle originally given in the sine or cosine function that has been squared, you double it when you convert it in the equivalent identity using the cosine function. So going back to that, if I go back to this question of mine, if the angle doubles, How will then the equivalent of the sine 1/2 x raised to 4 be written? Isn't this equivalent as well to, all right, it's equivalent. This is equivalent to sine squared of 1/2 x squared, right? Then how am I going to write this? In the double angle cosine equivalent, it should be the denominator is always 1/2. The first term in the numerator is always 1. Since this is a sine, it should be minus. Then what? Okay, so correct. So you will have here the double angle equivalent of 1/2 x. You double it, that would be x. So this would be cosine of x. Now, since this is squared, you also have this squared. Okay, that's correct, Mark. So you have 1 minus cosine x over 2 squared. Why squared? Because this is squared. You'll have this expanded the way it was expanded in here. And the rest is up to you to process already. So if you'll have this expanded, I'll write here the processing. The other side, it would be 1/4 times. So this one, if squared, is 1 minus 2 cosine of x plus cosine of squared x, right? Exactly the same as this. The only difference is your angle here is x. In here, your angle here is 2x. It became 4x here. So a while ago, I asked, do you have any questions? You did not even bother to ask a question why this became 4x already. Now, I ask you this one to write in the equivalent identity. You do not know. You have to be very observant, class, in the processes that are given or that is done to illustrate the evaluation of the integral. You don't memorize unless you understand the formula. You are required to memorize, but purely memorizing will not help, will not make you finish the job of evaluating a given integral. There has to always be a application. So this one, the squared cosine will again be converted. So you'll have here 1/4, 1 minus 2 cosine x for this. This is integrable. This is integrable. This one will be plus 1/2. That's a cosine. So that would be 1 plus cosine what? You double this, 2x. Now this time you can have it integrated because these are all simple already. So you have here 1/4, this 1 and this 1/2 gives you 3 halves. That's addition. And you have -2 cosine of x. And this is 1/2 plus 1/2 cosine of 2x. Now, these expressions are readily integrable. You can have this integrated, this can be integrated, this can be integrated using substitution, this can be integrated using power rule. Okay? Now, I have given you a glimpse of what it is when they mean trigonometric transformation. And we just have discussed only one type for now. Remember, I said there are around 6 or 7. So better understand this later on. Go back to your canvas, read on this particular topic. That way, when we meet each other next week, you will know what I am going to talk about. Okay, so I don't want to make it very, shall I say, mentally stressful for you today because this is the start of the second part of your module 2. But next week, you will be again given a quiz. A 1-hour quiz on what? the integration involving the natural log, the natural exponential function, and the general exponential function for the first hour. After that, I will continue with this. We will have a break, but I will not only discuss two types. I will not only discuss rather one type, but we will progress. We will discuss two types or even three types. So read in advance. That way you will not feel overwhelmed when I cover this particular topic to you already. I don't want us to cram during exam that if it's near the exam already, I have to bombard you of all the things that you need to learn. That way we can finish the topic. So we'll just take this slowly. We will increase the challenge every week. So you have a quiz followed by a discussion and a continuation of this next Monday. Okay, for now, you process the remaining part of the problem sets just in case you haven't processed them fully, and then read on this again. Do you have any questions for now, class? No questions? Are expectations for next week clear? I'll stop sharing. Okay. You have the rest of the hour break, or you can, after your break, you can go back to your Canvas and then spare time with your integral again. Okay, so bye for now, class. I'll see you again Monday next week.